tiller steering. Before anyone had figured out what driving a car even meant, the first automobiles were steered with a tiller, a horizontal lever borrowed directly from maritime navigation, mounted where a steering wheel would eventually go. The logic was intuitive to anyone who had sailed a boat, which, in the 1880s, was a more common skill than it is now. Push the tiller left, the front wheels swung right. This worked tolerably at walking pace on level ground, but it became genuinely dangerous at any real speed. The geometry that made tiller steering manageable at low velocity turned it into a liability as soon as the road curved or bumped without warning. Early motor races, rough, fast, and chaotic, made the problem impossible to ignore, and the automotive establishment responded quickly. By the turn of the century, steering wheels had replaced the tiller on every vehicle intended for serious use. The whole episode lasted barely 15 years, making it one of the shortest-lived major technology transitions in automotive history. Worm and sector. Among the earliest purpose-built automotive steering mechanisms, worm and sector used a spiral-threaded worm gear on the steering column that engaged a toothed sector gear connected to the front wheels through a series of rods and linkages. Turning the wheel rotated the worm shaft, which swung the sector through its arc and converted that motion into wheel movement. The design provided meaningful mechanical advantage, less effort from the driver for a given amount of steering input, and it was robust enough to survive what early road surfaces regularly handed out. It remained common on American cars well into the 1950s, partly because it scaled up reasonably well to heavier vehicles. The main limitation was imprecision. Play accumulated in the system as components wore, and the feedback that reached the driver's hands was vague enough that correcting a drift required anticipation rather than reaction. It was a system built for durability in a period when that mattered more than feel. If you're finding this useful, hit like and subscribe. More of this on the way. Recirculating ball. An evolutionary step past worm and sector, recirculating ball steering replaced direct gear contact with a loop of steel ball bearings running inside a grooved channel between the steering shaft and a worm nut. Those balls transferred load between the shaft and nut as they circulated continuously through a return tube. And that circulation was the point, since it eliminated the sliding friction that wore down earlier designs and caused them to become sloppy over time. The result was lighter effort at the wheel, longer service life, and more consistent feel across the vehicle's lifespan. General Motors adopted it widely in the 1940s, and it went on to dominate American car production for decades. Large vehicles benefited most because the system handled high steering loads without the structural compromises that plagued alternatives at the time. Trucks and full-size SUVs continued using recirculating ball steering well into the 2000s, long after passenger cars had moved on to something more refined. Rack and pinion. The architecture is almost self-explanatory once you see it. A small circular pinion gear on the base of the steering column engages a flat-toothed rack running laterally across the front subframe. Rotate the pinion, the rack slides left or right, and tie rods at each end push the front wheels through their steering arc. Fewer components than recirculating ball, a shorter mechanical path, and far less lost motion between input and response. The real advantage, though, was feel. Rack and pinion transmitted road surface information back through the steering in a way that earlier systems simply did not. Drivers could actually sense what the front tires were doing, which changed how cars were driven and how they were developed. European manufacturers, particularly German and British ones, adopted it early, partly for the performance emphasis and partly because their lighter vehicles made it feasible before it was practical on heavier American cars. By the 1980s, it had become the default for most passenger vehicles worldwide. Today, virtually every new car uses some variant of it. Hydraulic power steering. A fully manual rack works fine in a light car. Put the same system in a heavy saloon or an American land barge from the 1950s, and the effort required to park it becomes a genuine physical workout. Hydraulic power steering, which entered production on the 1951 Chrysler Imperial as a $198 option, solved this by coupling a belt-driven pump to the engine and using the hydraulic pressure it generated to assist the driver's input. In more developed systems, the assist was speed-sensitive, substantial at low speeds for easy maneuvering, reduced at highway speeds to preserve feel and directional stability. It worked extremely well, and the industry adopted it broadly over the following 2 decades. The trade-off was mechanical. The pump ran continuously off the engine, whether steering assistance was actually needed or not, consuming somewhere between 1 and 3 horsepower depending on the vehicle. On a long highway run in a straight line, that energy was simply being wasted, the pump pressurizing fluid that was going nowhere. Electro-Hydraulic Power Steering. The hydraulic circuit in traditional power steering was not the problem. It was what drove the pump. Replacing the belt-driven pump with an electric motor meant the hydraulics only activated when needed, rather than running continuously. The fluid, the pressure lines, the assist mechanism, all still present, just the energy source changed. That single modification produced a meaningful improvement in fuel economy compared to traditional hydraulic systems, typically in the range of 2 to 4%. Small in any individual trip, but significant across a fleet of millions of vehicles measured over years. It was also a practical intermediate step for manufacturers who needed the high assist forces that only hydraulic pressure could reliably deliver at a time when electric motor torque output was still too limited for the heaviest applications. Electro-hydraulic systems appeared widely through the 1990s and 2000s on larger cars and early SUVs, then largely faded once electric motor technology caught up to what the hydraulics had been doing all along. Electric power steering. No fluid, no pump, no belt. Electric power steering places a motor either on the steering column or directly on the rack and uses a torque sensor to detect how much assistance the driver requires at any given moment. The motor applies exactly that assistance and nothing more. When the car is traveling in a straight line with no steering input, the system draws essentially zero power. The fuel economy gains compared to hydraulic systems are measurable, typically 3 to 5% across a standard drive cycle, which matters enough to appear in manufacturer emissions calculations. Beyond efficiency, EPS opened something hydraulic systems could never offer: software configurability. Steering weight, response rate, and center point feel can now be tuned by mode, heavier in a sport setting, lighter in a city or comfort mode, all without changing a single piece of hardware. The persistent criticism has been reduced tactile feedback compared to hydraulic systems, a complaint manufacturers have taken seriously. The better-tuned examples from the past 5 years have largely closed that gap. Four-wheel steering. The front wheels do the work in conventional steering. Four-wheel steering adds independent movement at the rear, and the direction that movement takes depends on how fast the vehicle is going. At low speeds, threading through a car park, making a tight U-turn, the rear wheels turn in the opposite direction to the fronts, effectively shortening the vehicle's wheelbase and reducing its turning circle. Honda introduced a production version on the 1987 Prelude, demonstrating a measurable improvement in low-speed maneuverability that surprised reviewers who tested it at launch. At higher speeds, the logic reverses. The rear wheels steer in the same direction as the fronts, which stabilizes the vehicle during lane changes and high-speed cornering by reducing the yaw moment. Modern systems fitted to the Porsche 911 GT3, the Ferrari Roma, and several large luxury SUVs use electro-hydraulic or fully electric rear actuators with millimeter-level precision. A current 911 with rear-wheel steering has a turning circle smaller than a Volkswagen Golf. Steer-by-wire. Every system described above, regardless of how many layers of assistance were added, maintained a physical-mechanical connection between the steering wheel and the front wheels. A column, a shaft, a rack that could be traced hand to hand. Steer-by-wire removes that connection entirely. The steering wheel sends electrical signals. Actuators at the wheel ends respond. No column, no intermediate shaft, no mechanical fallback. The steering ratio, the feel, and the response curve are all defined in software and adjustable in real time. Infiniti offered a limited implementation, the direct adaptive steering, from 2013 onward, though a mechanical backup was retained as a regulatory compromise. Full adoption across the industry has moved slowly because the redundancy requirements are genuinely demanding. If the primary signal path fails, a validated backup must respond seamlessly, and proving that to regulators takes years. What steer-by-wire makes possible, variable geometry, complete column removal for autonomous packaging, and fully decoupled steering feel makes it the most architecturally significant shift in steering design since the tiller was retired. Which of these do you actually notice when you drive? Do you feel the difference between hydraulic and electric, or does it all just feel like steering to you? Comment below. Hit like and subscribe. The algorithm already has your next one queued up. Just click.